This is another re-evaluation of some of the claims in the literature. Generally, there's been a sense that global warming has been accelerating and that models are sometimes underestimating the warming and so on and so forth. There is a whole debate about why models don't do well this or that, but keeping that aside, just looking at data-based estimates of global warming, this paper looks at whether there is really a recent surge in global warming, and their conclusion is that there is no such surge detectable in data. So they take the data and they put it through statistical analysis of change point. How do you detect if there is a change in the rate of warming, and how long the time series has to be to actually detect a surge, and depending on the vantage point you have, how large the surge has to be for it to be detectable. So if you were sitting in 2024 and looking back, how many years would you need and how large the surge will have to be for it to be statistically significant surge? So it's kind of an interesting way to back calculate whether there's been a surge or not. The global mean surface temperature is widely studied to monitor climate change. A current debate centers around whether there has been a recent, so post-1970s surge or acceleration in the warming rate. Here we investigate whether an acceleration in the warming rate is detectable from a statistical perspective. It's not saying global warming is not happening. Be sure global warming is happening. It's about whether the rate of warming has accelerated. We use change point models, which are statistical techniques specifically designed for identifying structural changes in a time series. For global mean surface temperature records over 1950 to 2023 are scrutinized within. So there are multiple reconstructions of global mean temperatures, global temperatures, and there are reasons why people produce different products and how they extend it backwards, how they fill the gaps, and how they merge various sources of data, and how the data are merged with models in a reanalysis mode, and so on and so forth. Our results show limited evidence for a warming surge. In most surface temperature time series, no change in the warming rate beyond the 1970s is detected, despite the breaking record temperatures observed in 2023, and it's continuing in 2024, which we have discussed elsewhere as, not having a full answer yet for why it was so warm. Even when we add global warming and El Nino of 2023, the warming seems much higher than that. As such, we estimate the minimum changes in the warming trend required for a surge to be detectable. Across all data sets, an increase of at least 55% is needed for a warming surge to be detectable at the present time. So when the paper was being published, let's say the beginning of 2024, if they look back, how large will have the surge, how large does the surge have to be for it to be detectable by this change point model? So the message is fairly clear, but let's put some background on it. Global mean surface temperature GMST series are crucial for monitoring global warming. Warming can be quantified by change from a base period, so there is some pre-industrial period used typically, or by the rate of change, so warming rate over a time interval. The GMST naturally fluctuates in time, displaying short periods of accelerated or decelerated warming, as we'll see in a minute. So it's not unusual for it to have secular accelerations and decelerations, but if it lasts for so many decades after the 1970s, then is it real or not? That's the question. And remember, in the 1970s, a regime shift in climate was also claimed and has been documented in many papers, and is again argued to be statistically different, but that's a shift, not a trend, right? Or an acceleration of a trend or a surge. Considerable attention has focused on changes in the warming rate in the scientific literature and news media, with episodes of accelerated, decelerated warming, so surges and slowdowns, being recently debated. These fluctuations may happen in the presence of long-term warming as well as a background, and can arise due to short-term variability or noise in the surface temperatures. Here, trend means long-term change in mean temperatures, and noise contains fluctuations about the trend, which could be internal variability. So El Nino comes and bumps it up, volcano comes and pulls it down, and so on. Noise in temperature series is often characterized by a short memory process, such as an autoregression. In this other short memory models, the ocean and the other slow climate component systems respond to random atmospheric forcing slowly, producing variability at timescales longer than that of white noise, the classical Klaus Hasselmann model, where ocean can integrate weather noise because it's got high heat capacity and can store heat and release it on much longer time scales. Short memory fluctuations can be large enough to temporarily mask a long-term warming trend, creating the appearance of a slowdown. Okay. They can also exacerbate a warming trend, mimicking a surge. The key question then is whether these fluctuations are occurring without any change in the underlying warming trend, or whether there has been an increase or a warming surge or a decrease, warming slowdown in the trend. To answer such questions, one needs to model short-term variability in the surface temperatures. Obviously, things like AMO or PDO or multiple El Ninos in a decade can put a spin on the trend. So there is a background trend which is related, let's say, to anthropogenic forcing, greenhouse gas increases, and then there is internal variability. Can the internal variability actually add to the warming and accelerate it, or is it able to cool it and make it look like a pause in the warming? This debate has been going on because Eastern Pacific, which has remained cold for several decades, can damp the global warming, right? So is that a natural variability on top of the warming by anthropogenic forcing, forced trend, or is it part of the response to global warming? So several questions come up. Several studies suggested that a slowdown in warming, the so-called hiatus, occurred in the late 1990s and investigated its causes. The slowdown was attributed to several factors, including large-scale variability in the Pacific Ocean and external forcings that I just mentioned. However, studies focusing on the detection of this warming pause showed that the rate of change had not declined, and this period from approximately 1998 to 2012 was not unusual given the level of short-term variability present in the data. So what happened in the real world versus what is actually recorded in the data, right? More specifically, studies analyzing GMST using change point detection methods, which are specifically designed to objectively detect the timing of trend changes, showed no warming rate changes circa 1998. So warming pause is not a statistically significant change in the warming rate in that sense. Further, a study assuming that the change point time is known and took place in 1998 showed that the trends before and after 1998 were statistically indistinguishable. There you go. Overall evidence for a pause or slowdown circa 1998 lacked a sound statistical basis. So that debate has lots of papers you can go and read. So what are they doing? As I said, statistical change point model, short memory model, and so on. So here we are looking at multiple data sets. NASA had Groot, NOAA, and Berkeley. GMST anomalies from 4 data sets with superimposed piecewise linear model fitted trends. GMST anomalies from NASA had Berkeley with fitted trends for a continuous models with changing autocorrelation, discontinuous models with changing autocorrelation. The model fits only show the trend in different regimes. So without going into the technical details of what we mean by continuous and discontinuous models, you can see that the change happens here in the 1970s, and there is a change here that is slightly different, and the rates are different also, but each model also has a different rate, more so here, let's say because of more data being filled in the gaps as opposed to these periods where we have more data. So just the data coverage and the way they are reconstructed obviously could have an impact as well. That's why different products produce different results. Change points detected in 4 global mean surface temperature data sets then with continuous and discontinuous change point models. I'm not going into that statistical detail because it's not critical for the point being made. NASA 1973 in the continuous model and 63 in the discontinuous model, and you can see the trends before and after the change point are presented below the change point. So degrees C per year, 0.004 jumps to 0.020, 0.004 and 0.0019, so not really that different. Hadkrut 73-63, similar, 60, so different from each other but similar in the continuous and discontinuous model, except for the change point happens at different times. NOAA 1967 and 63, so 0.002 and 0.017, so this is definitely standing out here. You can see that, right? So Berkeley is more like Hadkrut and NASA. So why that is, you can go and try to read up. But if you look at an example of GMST time series with a spurious fit, a Hadkrut GMST in A, Hadkrut GMST anomalies in black with fitted superimposed discontinuous piecewise linear trends in red, calculated assuming independent errors, and B, scatter plot of the errors to illustrate a positive correlation. So zoomed in here is B to show the scatter plot correlated errors, and if you assume errors are random and uncorrelated, then you get a different answer. So you are doing spurious piecewise linear regression here, so going before the 1930s and after 1930s into 1970s and up to 98, let's say, and then so you keep on doing this and then try to see if there is really a warming surge. Warming surge, a question mark, right? So hypothesis test provides strong evidence that the independent errors assumption is not valid statistically significantly. So if you put confidence requirements, then it's not clear that independent errors assumption is valid when you do this. Then there are obviously consequences of that in making change point detection as well. Then they do the model extrapolation kind of thing. So observed versus predicted GMST anomalies for 2023. What would we, none of the models actually predicted the level of warming. What do these models say? In A, we are looking at GMST anomalies from the NASA, Hadkrut and NOAA again, and Berkeley series with superimposed piecewise linear model as we saw before. Okay, and you then do 2023 from observed, which is where is it? It's up here, and all the models underestimated it. Okay, so here are the anomalies predicted. So the fits displayed here include the autocorrelation. Model is fitted until 2022 and used to predict the 2023 data point. So there is a training period and a test period for each data sets based on the fitted trend and autocorrelation. Actual observations for 2023 are also presented in circles up here. So in NASA model, Hadkrut model, and the Berkeley model, and what their standard deviations or errors are. So if you look at the zoom in over 2023 with observations as circles and predictions as squares, they are all seriously underestimating. The observed 2023 anomalies are all outside the 95% intervals, indicating a large departure from the expected mean. So each data set has its own 2023 warming. Lots of debate about now whether 2024 is crossing 1.5 degrees C and so on, but the data themselves have different, slightly different values, and these are not small in terms of, if you reach 1.51 and claim that we crossed 1.5, and then between data sets there are such differences, then what do you actually do with it? I have a podcast on how Copernicus already put out a message apparently to help COP29 or motivate COP29 to work harder, that 2024 is going to be crossing 1.5 degrees C. So it's good to remember that science works this way, but sometimes maybe we are too excited to claim certain things like a surge in warming, and then somebody can go back and look at the data and say, well, statistically speaking, I cannot detect a surge really coming out of the data. Okay, so GMST series fluctuate in time due to short-term variability, often creating the appearance of surges and or slowdowns in warming. While these fluctuations may mimic an increase or decrease in the warming trend, they can simply arise from the random noise in the series. This is important considering the warming hiatus discussion over the last decade and the more recent alleged warming acceleration, especially when we keep saying we are crossing some magical threshold like 1.5. Formal detection of surges and pauses should account for noise or short-term variability and the additional uncertainty of identifying the change point times, unless the timing of a change point is suggested by independent model theory and observations. Here, several change point models were used to assess whether an acceleration in warming has occurred since 1970. Different change point model types were considered to assess the sensitivity to model choice. After accounting for short-term variability in the GMST characterized by an autoregressive process, a warming surge could not be reliably detected any time after 1970. Anytime. This holds regardless of whether the change point model imposes continuity of mean responses between regimes or autocorrelation is fixed or time varying. Okay, so that's the continuous discontinuous models. We further demonstrate that an acceleration is detected with a discontinuous model that assumes independent errors, which is not a statistically valid model choice because the method doesn't work in a statistically significant way. Model fit should be assessed for overall goodness of fit and produce residuals with a zero mean and no autocorrelation, which would make it a white noise. In the supplementary information, this is done by analyzing residuals from the model fits and testing them for residual autocorrelation. While our focus is on whether there has been a continued acceleration in the rate of global warming, our analysis recognizes how unusual surface temperature anomalies were in 2023. This is a big question now. Our model fit in the continuous mean response model with changing autocorrelation, as we saw in figure 1a, shows that 2023 anomaly is larger than the 99th percentile or the expected mean, indicating a large departure from the current warming trend. One could consider including exogenous variables such as ENSO in the model, which would reduce variability in the results and enable statistically detection of any changes sooner than 2023 to see if we have enough of a time series to see detect a surge already. The fact that trend changes in GMST records were not detected after the 1970s does not rule out that some small changes may have occurred. Indeed, the records may be too short or changes not large enough to be detectable yet amidst the short-term variability. This is why they provide a figure that I skipped about the vantage point year 2024, for example. Go back in time and see how large the surge would have to be for it to be detectable by 2024, and they give you some numbers, and those numbers are not met in the data that we are analyzing here. So it still leaves us with the answer that there is no robust, statistically significant surge detectable. The fact that trend changes in GMST records were not detected after the 1970s then does not rule out that some small changes may have occurred, as we said. Indeed, the records may be too short or changes not large enough to be detectable amidst the short-term variability. Emphasis. As such, a simulation study was conducted to assess when a warming surge will become detectable in the future. A change in the warming rate on the order of 35% around 2010 becomes detectable circa 2035. This is an excellent way to think about it. If a surge has happened and we are not yet detecting it, then when would we detect it based on the jump or the surge, the rate of change, that is 35% by 2010 to be detectable by 2035. This is the case for both an acceleration or a slowdown in warming. Our simulations show for either an increase or decrease in the trend, two-sided students t-test. Detection lengths would reduce with one-sided testing, say warming only, but this is not deemed justifiable given the recent discussion about a pause. So it's not just that you are not detecting a warming surge, but even a warming pause would be undetectable in this case, right? Indeed, testing for a warming increase because the same observations suggest an increase will tend to overstate the significance. Finally, our conclusion that an acceleration is not detectable at the global level yet may not apply at regional levels, and a rigorous detection of regional warming warming surges should be the focus of future work. So, obsessing about global mean and 1.5 can in fact miss the point that there may be some regions which are already over 1.5 and surged for a while. And some other regions are cooling for sure, because Eastern Pacific, North Atlantic, parts of India and so on. Our conclusions are based on piecewise linear models. While piecewise linear models provide a good first order approximation of any non-linearities and prevent overfitting the data, no model will perfectly describe our scenario. The assumption that global surface temperatures contain first order autocorrelation, which describes the dependency in the year-to-year noise values, is short memory and geometrically decays in year. Other types of models used to describe the noise in surface temperature observations include a long memory model where the decay is a power law. However, we do not consider these models here, as identifying a long memory requires long time series, and its presence tends to be more prominent in the sea surface temperatures and not land temperatures. Stochastic trend models where the GMST trend co-integrates with the trend in radiative forcings have also been considered. That said, these models have been mainly used for detection and attribution studies, and we focus on detecting a change in the warming trend here. Okay, so a lot of statistics, a bit too much maybe, but it's still important, because sometimes some messages get repeated again and again, and then the media thinks it's coming from good sources, credible sources, legitimate sources, so must be true, and they highlight certain things like the 1.5 degree crossing this year and the global warming acceleration that has been used repeatedly. So such studies are good to go back and say, wait a minute, we don't really detect any surge, or the surge is not long enough, or the data is not long enough sometimes to detect the surge, either to cooling or warming, not just warming. Okay, and the point is, if you are looking at the data that's showing warming, then you may overstate the surge because of the way you do the analysis. Anyway, it's a good paper, so I wanted to make the point, and hopefully it's helpful. Okay, see you in the next topic.